Hello, August 29th. All right, let's do this. Modify graph edge weights. Oh, I've done this before. Damn. Okay, undirected weighted graph. Connected. Containing n nodes labeled from 0 to n minus 1. Integer array edges. ABW indicates where the edge between nodes AB and weight. Some edges have the weight of -1, while others have a positive weight. Your task is to modify all edges with a -1 by assigning them positive integer values so that the shortest distance between the nodes, source, and destination becomes equal to an integer target. If there are multiple modifications that make the shortest distance between make it possible, any of them will be considered correct. Return an array containing all edges in any order if it is possible to make the shortest distance from source to destination equal to target, or an empty array if it is. I think there's some no, it's fine. Empty array if it's not possible. You are not allowed to modify the weights of edges with initial positive. All are negative. So that the shortest distance I mean, when they shortest, it's the weight, right? Okay, so but you have to modify. Hold on, let me see it again. Modify all edges with -1 by assigning them positive integers. So at least I had to assign them 1, right? And to make it equal to the. So what we have now, 4 to 1, 2 to 0, 0 to 3, and 3 to 4. And start with 3, ending at 1. And one way to go is this. Shortest distance. Basically, what it's saying is just if we do Dijkstra, or any of the algorithm, the Bellman-Ford, right? It's also, you have a start, and then you can go through everybody and then see if you can make it shorter. Yeah, but everyone has so I don't know. We get everyone to become 1. Because you say all edges has to be assigned a positive value. So we assign everybody to 1, and then we run it. I don't understand. Source is 0, target is 2. From 0 to 2, you go to 6 by modifying. What if 7? Can we do G like that? I don't think it's allowed. Yeah, I don't think it's allowed. Hold on. So this is negative, but what if I say target is 7? Now expected is still nothing because you cannot do back and forth because we only want the shortest distance. Okay, 0, 3 is -1. So yeah, that's what I said. You set it to 1 and you say from 0 to 2. The shortest is 6. No loops or repeated edges. So what if I just turn all the -1 become 1? Right? Then you have the shortest distance. You can find the shortest distance and then try to see if the shortest distance is larger than the target, then there's nothing you can do, right? But if the shortest distance is smaller than target, can we just make a change? But if you make the change, you have to verify again if that is still the shortest distance, because the shortest distance might change. That is a good point. That is a very good point. And there can be many paths, many edges along the way that is modifiable, right? Many paths is modifiable. So once you modify it, you might have changed the shortest distance. And we can do a modification and run Dijkstra again. And see if that's still the smallest. I guess I can do that, but is that the best way? Hold on, let me think again. But as you go Dijkstra, you can go Dijkstra from source to destination, and then you go through the whole Dijkstra. Then you have the minimum distance, right, from source to every single one, right? You can have that. From source to every single one, you have the minimum, and we can also have the parent. So now we have the parent, so we know the path from the source to everybody, the minimum so far. And by making changes to an edge, which is to make it bigger. so that it can fit. Because you want it still be the minimum, right? That's what you want. You want it still be the minimum. And it's not possible. I don't think it is possible to, because like for each one you have to make a change. For each one you have to make a change. Well, technically not each one, but each edge on the shortest path, you have to make a change. And by doing this change, I think what you need to see is the shortest path and the second shortest path. Right? Or we can try to find all the paths. Oh, it could be a lot of paths. We have the shortest path. Then we need to find the second shortest path. Because if we make changes to the shortest path, if it is part of the second shortest path, yeah, essentially what we need to know is if we modify, right? If we change some node, yeah, if all the paths, right, from source to destination goes through then you make change, you will affect everybody, so that will be fine. But if there are other paths, for example, in this case, right, we want 0 to 1, 0 to 1 to be 5, because there's only one path. But if we have another path, but they also say it didn't say there's no self loops. Yeah, we're going to do 0 to 1, right? If 0 to 1, we set it to some value, right? Now we set this as 5, but if this is 0 to 1, if it's, let's say it's a 2, right? Then this is not possible. No, that's not the case I was thinking about. I was thinking is the shortest path. If I make changes to bring it up, right, into a value, then your second shortest path is smaller. Yeah, that is, the second shortest path is smaller than your target. So your shortest path, second shortest path, both are smaller than target. And if you change one and you don't change the other, then the shortest path is no longer going to be target. Well, in that case, I can just make the other one bigger, right? I can make the other one bigger. So how about I set everybody to 1. I go shortest path. I find it. Okay. Then I have these edges involved in the shortest path, right? And all the other edges, I raise them to maximum value. Right? I raise them to maximum value. And then this is the only one because the shortest path, if it's smaller than target, right? And then I raise all the other -1 to gigantic value. Okay. And then I can trim them because they're just gonna be a giant value. So I trim those edges. And we don't consider those edges anymore because I only want to maintain whatever is the current, which is the smallest, right? Which is the smallest. Now, okay, so there are a few scenarios. One, the smallest does not contain -1. Then there's no way, right? There's no way because you cannot make changes, so that's an empty. If the smallest is larger than target, there's no way, right? So we eliminated these two. So the rest is the smallest contains a modifiable edge and it's smaller than the target. Okay, you can get that edge and you can get that path out. Okay, get that path out. You identify which one of them is the smallest, right? You identify which one of them is the smallest and which one of them is -1, which is modifiable. Yeah, you identify them. And for all the other edges, you treat it as a broken edge. So you will reshuffle the graph, right? When you redo the graph by going through, and everybody else is labeled as, just it's not an edge, right? It's not an edge. I have to figure out a way of how to do this, how to make this work. Yeah, because we have these edges, and we can have the edge, we can have this, and then we can do maybe create a new graph, and then as we go through, we'll remove the edge. Okay, we'll remove the edge, and then from start to the end, maybe by trimming the fat, I will be able to I'll be able to get it. Maybe by trimming the fat, I will be able to get it to run faster. You trim the fat, and then for the remaining, But there are also many ways to to fit the target. You can make increase in here, you can make increase there. How do I know if it's the right way? Right? You can trim some fat. But if you trim those fat, and remaining you have maybe a few paths. And you remove some edges and they're no longer part of it. Oh yeah, they're no longer part of it. The only one left is the only one left is the original one, is the one that does not have -1. Okay, maybe we can run it again. I don't know, what do you mean by run again? Yeah, we'll run it again to see the shortest distance. What is the shortest distance? If it's possible and it is smaller than target, right? Huh. Maybe that's the thing. We set all the -1. We just don't go through the -1. We run Dijkstra on it to see what is. Yeah. Okay. How about this? First step, we run Dijkstra on this. Okay, we run Dijkstra on this by setting the -1 to maximum value, right? To maximum value, and then we run Dijkstra, and what we're gonna get is what we're gonna get is the shortest path without using any modifiable edge, right? That's the initial without using the modifiable edge, and then we get the shortest path. Now if that path is smaller than target, then boom, no go, right? If that path is larger than target, that was good. Okay, then next we will run Dijkstra again, but with all the edges set to 1, right? And when we do that, we run it, we get a minimum, and if it's larger than target, there's no go, boom. But if it's smaller than target, that means we have one of the edges must be part of it. And all we need to do is identify the path and set everybody else to like gigantic value, and only those paths we can just make modifications. Yeah, make some changes. Okay, that seems to be a viable way of doing it. So now the goal is to implement it. Don't think it's an easy thing to do, implementing this, but we'll give it a shot. Edges. So what we want to do, what if we just do the graph? No, let's say int graph new int n by n, right? And then 0 is no edge, right? 0 is no edge, and smaller equal to 1, smaller equal to 0 is no edge. Okay, and what we need to do is for int edge of edges. Let's just say graph edge 0, edge 1 equal to edge 2. Graph edge 1, edge 0 equal to edge 2. Okay, so prepare graph. So next we're gonna do a Dijkstra. And the Dijkstra need to return a few things. Yeah, Dijkstra need to return a few things. So we're gonna say private int Dijkstra. So we need a graph for sure. We need int source. We have to go through everything, so it's actually no, we don't have to go through everything. The first time when you hit the target, the first time that you hit, it's going to be, yeah, the first time you hit the target, it's going to be good, right? The first time you hit it. You don't have to go through everything. The first time you hit it, so int destination. So this Dijkstra, we also need parent. Yeah, this is what I'm thinking. We need a parent. Okay, so Dijkstra in the priority queue. I think it's gonna be this queue. We need AB integer dot compare A0 B0. It's their weight, right? And dists. Okay, so we need n. N can just be graph. Okay. And we say arrays fill dists. Fill it with integer dot max value. Okay, then dists source is equal to 0. Q dot add new int 0 and source. Okay. While Q is not empty. Right, while Q is not empty. What do? We say temp go to q dot poll if temp current node is temp 1, current dist temp 0. Okay, so we say if current dist is not equal to dist's current node, continue. All right, otherwise for int child equal to 0, child smaller than n child plus plus. If graph current node the child is larger than 0, right? If it's larger than 0, which means we have an edge, and dist's child is larger than current dist plus graph current node child, right? This is the distance, and the distance plus the current distance is the new distance. So if it's smaller than whatever is already recorded, then we say dist's child equal to current dist plus graph current node child, right? And then we say q dot add new int, int new dist current dist plus graph current node child. Okay, so we can do this new dist new dist, and then we'll put new dist here and child. Right, so add this and just keep going. Well, also parent child equal to current node. So yeah, so we just keep going, and then at a certain point we'll say if current node is equal to destination, then we break. Now we return dists destination. So what is interesting in this case is we return the minimum dist from source to dest, but also modify in place the parent array so that we know what the main path is from source to dest. So that's kind of, we do two things at the same time. So we have this, right? Then then we can say original min distance shall equal to Dijkstra graph source destination new int n. Don't really care because initially this one doesn't really care. Oh, we can actually do this. Int parent new int, right? Doesn't really matter. We'll assign everybody to -1. So array dot start dot array dot fill parent -1. Okay. Parent. Except for parent source equal to source. Holy crap. It doesn't matter, we know where the source is. We go destination, just go down. Yeah, it's fine. So we do that. And then we'll go to this. So this gives me the original minimum distance, which is just unchangeable, right? So we say if original minimum distance is smaller than target. Okay. If it's smaller than target, hold a second. Comes equal to an integer target. Yeah, so if the original is smaller, that means there's no way we cannot do anything. right? We cannot do anything because it's small. No matter how you do, it's gonna be bad, right? And if it's bigger, then yeah, we set it to 1, and then we go to smallest, and then we just set, yep, hold on. So we say if this is smaller than target, then we return new int edges dot length 3. Yeah, not possible because the original edges already produces alright, this is actually causing a lot of issues, so I'm gonna do this. Because the original edges already produces the shortest, produces a min dist shorter than target. Right, so that's that. Otherwise, it's good, right? And then what we're gonna do is, yeah. Then what we're gonna do is now set all the negative edges to 1 and see and check the min distance. Again, erase the fill, parent with -1, right? Int, now the original minimum distance, now is modified minimum distance of 4. Right, then we say graph edge 0, edge 1, set to 1. Ooh, if edge 0, 1, 2 is smaller than 0, then we say this, right? And then modified distance shall equal to Dijkstra graph, again, source, destination, and parent. If modified this is larger than target, return new int. We probably can get int res equal to a new int edges dot length 3. So now we can just say res. Alright, this one is same, res. And the shortest distance after setting all negative edges to the smallest possible positive edge, and the min distance is still larger than target, it is also not possible. Right? Then it is possible, right? Then we'll say then we'll say set all keep the main path unmodified and set all the other edges to max. Right? Set all the other edges to max. And the max is the maximum weight. What's the target? Target is 10 to the 9th. Nah, we can set. Yeah. Yeah, we set everybody to max, and then we just need to adjust the min path to make it reach target. Okay, so I have the min path. Alright, we can go path all the way down. So every time we go, so we shall first set everybody to, so we're gonna copy the edges. Right, we copy the edges. So we say for int I equals 0, I smaller than edges dot length I plus plus. We say res I equal to new int edges 0, edges 1, edges 2. Right, this is just to make a copy. Now after this copy, sorry, right, now after making this copy, then we're gonna check int node equal to destination, while node is not equal to source. Int next node equal to parent current node. Okay, then how do you know it is modifiable? Shoot. Modifiable. Yeah, how do you know it's modifiable? Well, I mean, I already know it, right? If I already know it, hold on, if I already know it, I don't need to, I can just reset the graph because it's fine, right? I'll just reset the graph. How about that? I can just reset the graph. I don't need a graph anymore. Actually, this is not what I want. H2. Right. I don't need the graph anymore. So we use it to mark which edge is modifiable, right? And then we get the next node. Then we say if it's modifiable, right? We say if wait, hold on. What are you trying to do? Okay, what I'm trying to do is hold on. What are you trying to do? What I'm trying to do is to find out this path, right? To find out this path, to record which one is on this path is modifiable, right? And we will make a change to it, right? We'll make a change to it. And then okay, hold on. I don't do this way. Okay, I don't do it this way. I do the same edge of edges, right? I don't do it this way. I say if edge 2 is smaller than 0, right? Then I'll set everybody to maximum. So that's what we want, integer max value, right? I set everyone to integer max value. Okay, so everyone gets set to max value. Now we go through this, right? We go through this, yes, and then we say if graph node to next node, if it's equal to integer from max value, then we will set it to what? I don't know. Right, I don't know. I do diff shall equal to mod min dist should be target minus mod min dist, right? And then we say if diff is large or equal to 0, then I set graph node next node to diff plus 1, and diff, I use it, assigned to a negative value. Else graph node next node just assigned to 1. And everybody else leave unchanged, okay? You probably need to assign it twice. Yeah, I had to assign it twice. So next node. Alright, this is the same thing. Having to assign it twice. Alright, so once this is done, now what I can do is, holy crap, I have to go through everything and assign all the graph values not 0, right, into nope, I can do this. For int I 0i smaller than edges star length I plus plus, right? I can say edges I. If edge 2 is smaller than 0, actually no. I'm going to say res I new int edge 0 edge 1 graph edge 0 edge 1, and then we'll return res. Ooh, let's see. Will be interesting. Huh. That is not expected, but it's okay. I think we just have a misunderstanding. Expected is empty array. I don't understand. How do I return empty array? Yeah, that is a problem. We'll deal with that problem. Hold on, let me make sure. So we put this here. So this is not res empty array. What, new int this? What's empty array? Java empty array. Maybe I can do that. Let's say new int 0. Let's see. Maybe I do this. Can I do this? Okay, this is cool. All right, let's try the others, see if it works. Some infinite loop has been detected. Where is the infinite loop? It could be here because I think I forgot to set. Right, if this is equal to max, so I reset the value. If it's not, then I don't change, and what I'll do is say node equals next node. Okay, I did forget something. All right. So my first is to set for 1 to 3. Two zeros, and then 0, 3 is 1. This is 3 is 1. All right, let's give this a shot. Ooh. I think this is... But it says... Oh, wait, hold on. Oh, in the range of 2 to the 9th. 2 times, okay, so we have to get a max value. Let's try int max. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so instead of integer on max, we should do this on the outside. Actually, this is fine. This doesn't affect. So all we need to do is to assign this to max. Assign this to max. Well, this one considered correct. Yep, this one considered correct. Just need to set to max. Okay. Try it again. Oh. Alright, that doesn't seem right. Okay, we need to check. We have 0, 1, 2, 0 is 2. 3, 2 is 6. 2, 1 is 10. 3, 0. Damn, 3, 0. So let's put 3 here. 3, 0 is negative 1. Alright, so target is 12, I saw. Source is 1. Destination is 3. So this is source, this is destination. Okay. So I put 0, 1 is 1. I put this is 1. And 0, 3 is 11. This is what I put. But expected is this is 11, is y. Yeah, so my going is 0, 1, 2, 3. Right, we'll have 10, 1, 11, 2, 6. From 1 to 3, what's the shortest distance? 1 to 3. 1 to 0, 0 to 3, that's 12, right? There's another way? Oh, there is another way. This. 9. Damn. Alright, so what I did initially is I leave them as negative 1, right? Initially, I leave them as negative 1, and I find because this cannot go. So now I have this cannot go. So that's the initial. Right, original is and then I set everybody to 1. I set everybody to 1. If I set everybody to 1 and the minimum distance is 2, right? This is minimum distance is 2. Minimum distance is 2. And I say, yes, that's good, right? It's good. But what I didn't do is the minimum distance also. Yeah, that's the thing, right? That's the thing. Because other paths also involved. I don't know. We can go one by one. Change one into diff, and then everybody else. We just run Dijkstra again and again and again. Yep, we just run Dijkstra again and again until we find one. It's a little bit desperate right now. Yeah, this is even more desperate. I don't even know what this is. Okay, so okay, node and this. We need to get list critical edges. Right, we have critical edges. Then what we do is, yeah, we do this diff we can deal with it some other time. It doesn't really matter. What we want is this. If it's this, we'll set it to 1. Okay. And critical edges dot add new int node next node. Right? And then do this. Then we get all the critical edges. So next, for each critical edge, I'm just gonna set it to the target value. Right? Set to the target value. Then we say for int critical edges of critical edges. And we say graph C0 C1 equal to target minus modified min_dist plus equal to. All right. Then we say if Dijkstra graph source destination doesn't have, the parent doesn't really matter. If this is equal to target, right, then we will do this. Right, we'll do this. We'll do this, and I'll break. And I'll after do this, then we'll return res. Right, we'll return res. Otherwise, we'll set it back and then try it again. I mean, basically just reset it to 1. And if at the end it's not possible, then we say new int 0. Right. Try modify the critical edges 1 by 1 and see if any of them would satisfy the requirement. Oh, okay, let's try this. Okay, satisfy all this. This time, my only concern is in my timeout. Loop. All right, this is definitely not the right way. All right, I'm gonna give up. This is not happening. I'm gonna read the solution, but it's kind of late, so I will do it later. Need to train. I'll see you guys tomorrow. Adios.